First off, we wanted to thank all of you that have signed up for our TechStar T3 series for webinars. Marketing doesn't look like they're going to be helping us. I wonder what in the world they were thinking, putting us on our own. But we put a good presentation together, we think. Hopefully we'll have some fun and give you some knowledge. We are presenting live from our Deer Park Service and Training Center. And with that, we are going to be talking about thermocouples and RTDs. So we've titled the presentation A Practical Guide to Improving Temperature and Measurement Accuracy. So the goal of this presentation is to share some common facts that will affect the accuracy of almost every temperature installation that you have. And we're going to do that so that hopefully you'll be able, number one, to pick the proper sensor, and number two, have an appropriate expectation of just how accurate the measurement's going to be. So to accomplish that, I'll give a brief introduction of myself and TechStar for those of you that may not know us. And I'm also going to introduce Dane Nelson, who's with More Industries, and we'll be sharing the presentation. Can we go to the next slide, I guess? My name is Jay Murray. I've been with TechStar 10 years. I specialize in upstream and midstream oil and gas. TechStar is going on 20 years. It's a specialty manufacturer's representative. We sell products for instrumentation, automation, and analytics, cover multiple markets. Oil and gas obviously is a large market for us. We also cover wastewater, food and beverage, and maybe a couple other markets as well. What makes TechStar a little different than other rep firms is we limit our product lines. We want to make sure that we can provide technical assistance and service that equals or surpasses the factory. So we literally have hundreds and hundreds of hours of expertise within our family, and that helps us to support the products. I have the list up there. I mean, we'll go over it quickly. By the way, our website is www.techstar.com. Vega, Level, Yokogawa Field Instruments, MSA, and General Monitors. They do flame and gas, KPG, some specialty upstream products, Fluenta for flares, SKF, equipment protection. K-Patents does some neat product identification. Fox Thermal, More Industries we have here. They have been known for many, many years, and Dane will give you some information on them as well for isolators, and also make excellent temperature devices. Signifier is a good wireless company. Michelle is for industrial moisture. And TAS is our sister company. This is another plus that TechStar have. We have our own internal systems integrating services so that we can provide a full system. More details to follow. Thank you for your time. Dane, can you introduce yourself?
Okay, so yes, my name is Dane Nelson. I work with More Industries, and More Industries has been in business for 50 years now, and we have multiple lines of products, isolators, alarm trips, safety line, pneumatics, remote I/O, HARP products, etc. But today we're going to be focusing on our temperature line, or rather details and techniques for measuring temperature more accurately.
I forgot to tell them about questions.
Oh,
yeah. So anyway, it's going to be an open format. What we're going to do is you just click on the question box, and then we'll try to take care of the questions as we progress. So we've got close to 30 slides, and we're going to get through those, and we hope that we have enough time that we can do some hands-on demos as well.
Yeah, so if you do have any questions, feel free to write them in the chat box immediately, and we don't mind stopping to cover those as we go. Or if I start covering a subject too fast, feel free to stop us, and we can elaborate on any details you might want and answer any questions you might have. But with that, we'll go ahead and get started and give you some techniques to help you with your temperature measurements. So one question that I ask whenever I'm giving this presentation to a live audience is, do you have the need to measure temperature accurately? And being that our customers typically have different processes, different applications, the answers are pretty widespread, but one answer kind of sticks out, and that's that no, we don't need to measure temperature accurately. Plus or minus 1 degree is okay for us. And that kind of helps me out in letting me know that perhaps that person doesn't truly understand or appreciate some of the hardships of measuring temperature and what we have to do to get within a degree of measurement accuracy. Plus or minus 1 degree of temperature measurement in a process environment is actually a very precise temperature measurement. And we have to do just about all the techniques that we're going to discuss in this presentation correctly in order to obtain that plus or minus 1 degree of uncertainty. So again, there's a lot of processes that we're taking the temperature of that that we don't need to measure accurately. Some processes need an accurate temperature measurement, and some we're just looking for spikes or different trends over time, something that might indicate some type of failure for us. But at the end of the day, some of the same techniques that we use to achieve accuracy result in less measurement drift. So if calibrations are important to you, if a preventative maintenance schedule for your temperature sensors and transmitters is important to you, then you might implement some of these techniques as well, even though it might not be a high accuracy temperature measurement that you're trying to take. So we can reduce drift by selecting the right transmitter or selecting the right sensor, using correct wiring techniques. All of these things that reduce drift also mean fewer calibrations for you, which is less operating expenses. So it saves you money just by improving accuracy and eliminating the drift in your temperature measurements. So what we're going to discuss today, we're going to talk about selecting the best sensor for an application. We're going to talk about how you might reduce error caused by external environments, reduce the error that might be caused from a lead wire for a thermocouple extension wire, RTD extension wire, and how to reduce measurement error at the measurement source, so at your transmitter, and then we'll discuss how to calibrate transmitters and sensors to each other to get a more defined temperature measurement. So in this application on this slide here, we've got a process where the production team has come to us and told us, hey, we have a goal of being within plus or minus 4 degrees Fahrenheit in order to have a successful process. So we want to measure this vessel uniformly. So we're going to have 2 temperature sensors implemented here. And we know that one of the American standards we use for thermocouples tells us that a type J thermocouple out of the box in perfect operating conditions has an uncertainty of plus or minus 4 degrees Fahrenheit. So right out of the box, these thermocouples, using 2 of them for this measurement, are not going to yield accuracy and be within the production team specification of plus or minus 4 degrees Fahrenheit. So right out of the box, we're not able to achieve this. So we can do a few things in order to obtain an acceptable tolerance for this temperature measurement. We can calibrate our sensors to transmitters to reduce the uncertainty, or perhaps we can choose a different sensor entirely that better fits the application. So if you use a 100 ohm platinum Class A RTD, we have an uncertainty of plus or minus 0.7 degrees Fahrenheit. If you use 2 of these RTDs, you're looking at an uncertainty of plus or minus 1.5 degrees Fahrenheit, rather than your plus or minus 8 degrees, which you might have with the thermocouple. So this is assuming perfect conditions right out of the box thermocouples or RTDs. These are standard uncertainties that any thermocouple or any RTD is going to have. So it's not like looking 2 years down the road for this application where you might introduce some external elements such as corrosion or anything else, any human error such as long wire runs. None of that might be contributing to the uncertainty at this point. This is just right out of the box. So in order to have a accurate temperature measurement and in order to have an acceptable range of tolerance, we have to consider not only the sensor itself and what its uncertainties might be, but the eventual problems that could occur due to corrosion or human error down the line. So discussing tolerances a little bit more and selecting sensors a little bit more, I wanted to go into thermocouple uncertainty, and this is due to an alpha curve in the millivoltage reading that we're taking from a thermocouple that we're not able to fully compensate for when we're reading a temperature. So if you look at the column marked 300 degrees Fahrenheit, with a type J or type K thermocouple, which are industry standard thermocouples, we have an uncertainty of plus or minus 4 degrees at that 300 degree operating condition. At a 900 degree operating condition, those two thermocouples have a 6.5 degree Fahrenheit of uncertainty. So this is saying that essentially at 300 degrees, your thermocouple could read up to 8 degrees off and still be within its normal operating specifications. Now, with anything, you can spend more money and get a better grade. You can get the Chevy or you can get the Cadillac. You can always go up in value and what you're paying for. And with thermocouples, that's not any different. So if we use a special grade thermocouples, a type J or type K thermocouple, uncertainty now reduces to 2 degrees Fahrenheit. So essentially cuts it in half from the 4 degrees of uncertainty that we had with standard grade wire. What this special grade wire is essentially more pure metal alloys that are being used to make up the thermocouple components. I didn't cover this at the beginning, but a thermocouple is made up of 2 dissimilar metal alloys. They see a millivoltage gradients across them whenever heat's applied, and that's how we take our temperature, by reading that millivoltage difference. So by using more pure metal alloys, we can reduce the uncertainty that we're seeing from a standard grade thermocouple to a special grade thermocouple. Now, RTDs are a little bit different than thermocouples in how they read the temperature, and we'll get a little bit more into that in a minute, but essentially they're reading resistances. Now, just like thermocouples and having the ability to purchase special grade materials, you can buy a Class A RTD, and that's going to increase the accuracy comparatively to a Class B or Class C RTD. So we can see with a Class A RTD at 212 degrees Fahrenheit, our uncertainty is 0.63, plus or minus 0.63 degrees Fahrenheit. So that's quite a bit of a difference from the type J thermocouple that we had with our special grade thermocouples, and a huge difference from the standard grade thermocouple type J that we had. So effectively, you could say that from going from a standard grade thermocouple to a premium grade thermocouple, we cut our uncertainty in half. And by going from a premium grade thermocouple to a Class A RTD, we effectively cut our uncertainty in half again. So this goes back to selecting the right sensor for your application and selecting the sensor that's going to yield the best results for what you're trying to accomplish. That plus or minus 4 degrees Fahrenheit with the type J standard grade thermocouple might be perfectly acceptable for your operating conditions and application. However, if you're looking for a more precise temperature measurement and an RTD fits into the operating temperature ranges, then we highly recommend using a 4-wire RTD for that purpose. So just like thermocouples that have an uncertainty, thermocouple extension wire also has an uncertainty. And just like thermocouples have a standard and a premium grade, thermocouple extension wire also has a standard or premium grade. Again, this is just looking at the metal alloys used to build the thermocouple, and the standard grade is going to be less pure metal alloys than the special grade. Effectively, as shown with the standard grade thermocouple and special grade thermocouple, the extension wire cuts the uncertainty in half as well. You can see here we go from 4 degrees Fahrenheit of uncertainty down to 2 degrees Fahrenheit of uncertainty. And again, all of this is assuming that these wires are not yet contaminated or corroded and are right out of the box in a perfect temperature environment. So this very well could be out of specifications. Do we have a question?
Yeah, we sure do. Gentleman is asking about certifications. And the other thing I wanted to point out is that the thermocouple extension wire is really specialty wire. It has to match the same material. So,
yes.
And it's not a cumbersome process, but a detailed process to make sure you have special connections and other things. But you want to cover that about if almost all of our products do have a certification. There's an adder, and typically the way that Moore would do a certification is typically they would put it in a temperature bath and give you the actual readings out. And you could also go ahead and order matched so that your 4 to 20 milliamps would equal that and you get a cert.
Yes, yes.
Other than that, you just, if you don't, then you just get the standard thermocouple table.
Yeah.
So plus minus 4 degrees.
Upon request, we will deliver a certification of the calibration of any sensor and transmitter as well. So we can provide that. So one question that I ask is how do you know how much air might be introduced by a thermocouple extension wire, or do you check the thermocouple extension wire? Thermocouple extension wire can fail just as thermocouples can fail, or as we discussed in the previous slide, thermocouple extension wire could corrode and induce error into your temperature measurement over time. So there's ways that you can check the error in your thermocouple extension wire and your thermocouples by reading your thermocouple calibrator at the receiver terminals and noting the reading. You then connect it up to the sensor end of the thermocouple extension wire, and you can make the same readings, and it'll let you know how bad things are. But another way that we can reduce the amount of uncertainty that's induced into our temperature measurement is by eliminating thermocouple extension wire altogether. We can do this by wiring directly into transmitters or remote I/O devices. Most of these accept any RTD or any thermocouple, and they reduce the extension wire that puts error and uncertainty into our temperature measurement. So by wiring directly into a transmitter, we reduce the need for that additional wiring that's going to eventually over time corrode anyways. So we reduce the uncertainty as well as eliminate a future problem for us. So there's times where we want to use an RTD. And an RTD is a resistance temperature device that measures a resistor, and as the temperature rises, the resistance will also rise. Many people think that RTDs, by definition, can't have lead wire imbalance, and what an RTD is measuring that resistance in an RTD element. And with a 2-wire and 3-wire RTD, we're actually measuring the lead legs. So those lead legs contain copper wire, which by nature is a resistance. So RTDs can have lead wire imbalances. They can corrode and be a contributor of lead wire resistance changes over time. They might have loose terminals or lead wire gauge intolerances, human error. All of these things can contribute to temperature measurement error due to lead wire compromise. So here's why a 4-wire RTD is the best suited temperature element for reducing the amount of uncertainty. With a 2-wire RTD, what we're effectively doing is running a voltmeter across an RTD element. And we're measuring that resistance and solving for Ohm's law with our voltmeter, and that effectively gives us what our temperature is. Now with the 2-wire RTD, we're passing this constant current source over this RTD so that we're able to solve for Volt's law, or so that we're able to solve for Ohm's law. If we're trying to get voltage, we need current and a resistance, and if we're trying to solve for resistance, then we'll take the voltage over our known current. So with the 2-wire RTD, you can see that we actually are including this lead leg here, R1, and this returning lead leg, R4. Now, since we're trying to measure a resistance in an RTD element, and we include the lead leg and the returning lead leg, R1 and R4, our temperature measurement's not very accurate. We're including additional resistance into our RTD calculation of what a resistance means in terms of temperature. So if we add resistance to that, by nature, our temperature is going to be higher than what we're actually measuring at our process. This led our industry to develop the 3-wire RTD. The 3-wire RTD introduces an additional leg that's high impedance and has no current flow in it. So essentially, there's no voltage drop over that third leg. So now when we're passing that constant current source over our RTD element, we're taking the resistance of the leg R1, and we're taking the resistance of the leg RTD and R4. Where the voltmeter leads in, that includes RTD element and R4 as the resistance that we're capturing in that measurement. So this is a pretty accurate temperature measurement if the lead leg R1 and R4 are identical. But Murphy's law tells us that that's never going to happen. They're always going to have some differences, and there's always going to be a little bit more corrosion on one wire than there will be on another wire. And so with that, we know that R1 and R4 will never be exactly equal. And since they aren't equal, and we're including R4 plus RTD minus R1, we're not going to get an accurate temperature measurement because we're including that resistance in the lead leg and trying to subtract an amount that doesn't equate to the amount that we're adding into our measurement. Now, shown here, I just have a short chart that I wanted to go over to let you know that if we have just 1 ohm of imbalance, that results in almost 4.7 degrees Fahrenheit of error. So just 1 ohm of differences between R1 up here, the resistance in this lead wire leg that we're measuring, and the resistance in this lead wire here that we're not measuring and that we're actually guessing at. Just 1 ohm results in 4.7 degrees Fahrenheit of error. So that adds up pretty quick if there's more corrosion on one wire than the other, or if we're having some type of problem guessing what that R4 leg might contain in terms of resistance.
We had a couple questions on accuracy, and I think we can try to cover those on our hands-on report. So we want to know that we're not ignoring the questions. We're just going to go ahead and try to cover it when we do our hands-on presentation.
Okay. So the 3-wire RTD is a fairly accurate temperature measurement, but it's not the most accurate. There is a way that we can eliminate that lead wire leg from the equation entirely and not have to guess at that other lead wire leg. And that's by using a 4-wire RTD. A 4-wire RTD has 4 leads now instead of 3. And you can see that the 2 high impedance leads right here are only measuring the resistance in the RTD when we pass the constant current source across it. So we're no longer taking the resistance in lead R1, lead wire leg R4. Those are both eliminated from the equation entirely. That's why a 4-wire RTD is our most accurate and does not have any lead wire compensation errors that a 3-wire or 2-wire RTD do have. So just kind of going back over 4-wire RTDs, the error or drift caused by lead wire is eliminated by using a 4-wire RTD. Again, we're only taking the resistance in the resisting element, which is telling us the temperature. So there's no longer any compensation being taken from R1 or R4. The accuracy and stability of the measurement is down to the RTD and the measuring circuit selection. Most don't know this, but 4-wire RTDs cost about the same as 3-wire RTDs. And it's important when ordering RTDs to specify if you might want a Class B or Class A sensor. Most manufacturers, by standard, will send you a Class B RTD sensor. You might have to specify a Class A sensor. So most modern transmitters and remote I/O accept 4-wire RTDs as standard. And the use of 4-wire RTDs essentially costs nothing more. So there's not too many good reasons to not use 4-wire RTDs, other than perhaps legacy equipment not accepting 4-wire RTDs as an input. I know that some legacy equipment, older equipment, or some dual input equipment even only allow for 3-wire RTDs. So if you must use a 3-wire RTD, we suggest using a 1000 ohm platinum RTD, 3-wire RTD, rather than 100 ohm. And in the chart next to this graph on slide, you can see that our error on the far right column of this, 1 ohm of error with 100 ohm platinum 3-wire RTD yields 1.5% error. With 1000 ohm platinum 3-wire RTD, that's reduced by a factor of 10. So now we're at 0.156% error. So that cuts down on our uncertainty by a fairly drastic amount when 1 ohm of imbalance creates 4.7 degrees of uncertainty. So I told you that we're measuring thermocouples in a millivoltage measurement. And with resistance, we're measuring the resistance, which is an ohm measurement. Those are both very low-level signals. And being low-level signals, they're susceptible to noise. It doesn't take a lot of noise to distort those low-level signals. So we recommend, in order to get a more accurate temperature measurement, using things such as drain wires and ground wires, and best practices to keep that noise that comes off your motors or VFDs, to keep that noise off of your low-level signals. Or we suggest reducing the extension wire altogether. Again, converting that low-level signal to a 4-to-20 analog, or perhaps a digital signal of some type, HART, RS-485. They're all high-level signals that are affected less by the same amount of noise that a low-level signal, such as a thermocouple or RTD signal, might be distorted. So we also have external influences that affect our temperature measurements. And sometimes we go into a specific application based off of convenience. That's what I have shown here. And I don't know if y'all can see this, or if we're gonna be able to zoom in on this. But what I have shown in the images on the presentation is sometimes we grab a sensor that just works because we need a temperature really bad, and effectively you have a heat sinking problem. We know that Murphy's Law also tells us the ambient temperature where this portion of your thermocouple or RTD might be sticking out, that ambient temperature is always going to be different than our process temperature, just because that's our luck, right? So since that ambient temperature is never exactly the same as our process temperature, any portion that's not in your process measurement is wicking heat away from that process measurement at the junction point. So we have a solution to this, and our solution is very simply getting a temperature sensor, such as a worm, which I have here made by More Industries, but any temperature sensor that fits the process application needs. So with this specific sensor, we're able to insert the entire sensor into the thermal well, and we no longer have some existing portions outside that's in ambient conditions that's messing up the temperature measurement. So looking at modern transmitters and I/O, most temperature transmitters on the market have very similar specifications these days. But some things that perhaps you should look into for high accuracy temperature measurements are maybe input resolution. Input resolution is something that you want the highest available. 20-bit resolution is what we have on More Industries temperature transmitters. And that's an industry best practice standard. So the input resolution is going to allow you to see more defined step changes in your temperature process. Long-term drift, how repeatable is that temperature transmitter over time? So this results in fewer calibrations with a longer drift accuracy temperature transmitter. The RTD excitation current. So we want to make sure that that RTD excitation current is as low as possible so that we don't accidentally heat our RTD element with the constant current we're passing through it. Yes. No problem. So input impedance for thermocouple inputs. And then sensor advanced diagnostics as well. So looking at different features such as sensor drift over time, wire corrosion, broken wire detection, all of those things might be important in selecting the correct transmitter when you're measuring a high temperature or high accuracy temperature process. So every RTD or thermocouple has some remaining error in it. Now, this is just due to us taking a coefficient that I mentioned earlier and applying it to a millivoltage or a resistance and expecting that to equate to an exact temperature measurement. Being that there's human errors and that that there's always some element of our temperature measurement that's not 100% perfect, these errors could be caused by the purity of metals used, or could be caused by the length of extension wire. So there's always going to be a little offset from our ideal curve to our RTD and thermocouple curve, but there's ways that we can get our RTD and thermocouple curve more defined to our ideal curve. At More Industries, we use a precision bath calibration for our sensors. So effectively, we take the temperature sensor and put it in a hot oil bath at one precise temperature that's within plus or minus 0.003 degrees Celsius. And then we calibrate a transmitter and that sensor to that defined temperature in the bath. We then take another operating temperature that our customer might provide us and calibrate at that temperature. So we have two defined temperatures that we're calibrating the sensor at. And we know that the precision bath sensor temperature is within that 0.003 degree of uncertainty. Now, what this does for us is it actually yields a trimming of the RTD or sensor accuracy of 0.02 to 0.03 degrees Fahrenheit. So this gives us a lot more accurate of the temperature measurement. And this is another way that we can calibrate the final controllable error out of our transmitter and sensor combination. One other way that we can reduce the amount of uncertainty in our temperature sensor measurement is by converting that low-level temperature millivolt signal and resistance signal to a high-level analog signal or a digital signal. So once you convert your temperature to a digital signal, we highly recommend keeping that signal digital because of the amount of information available on digital protocols and the speeds. So being a lot faster, we reduce the opportunity to have an error going from digital to analog and back from analog to digital. Modbus and over Ethernet or serial is another way that we can convert our thermocouples and RTDs to digital signals. Again, thermocouple extension wire is a very low level signal and is an antenna for noise. And if not protected or not converted to a digital signal or high level signal, it will be susceptible and yield an inaccurate temperature measurement. So going back over kind of what we discussed, some of our techniques to measure temperature more accurately include using a 4-wire RTD whenever the temperature allows. One of the constraining factors to RTDs is that they can only go up to a certain temperature, and most temperature specifications are around 800 to 900 degrees Fahrenheit. So we recommend using that RTD whenever the process temperature allows it. There's some times where you can't get away from using thermocouples. And so if you are using thermocouples, use premium thermocouples or premium extension wire. If you're using long thermocouple extension wires, make sure that it's noise protected so that it's not susceptible to the VFD noise or the motor noise that we discussed. Try and get rid of thermocouple extension wire as soon as possible by implementing transmitters or remote I/O or rather than direct wiring. Eliminate ambient temperature influences on your measurement. We do this by selecting the correct sensor. So I showed you our worm, but selecting a sensor that's appropriate for the job and not convenient for the job. Using sensor trimming, and our sensor trimming is the bath calibration. There's also what's called the calendar Van Dusen sensor trim that uses a few different variables that are added on to the thermocouple curve to make it more precise for the operating conditions. Buying the highest resolution, most accurate, and most stable temperature transmitter or I/O that you can afford. Again, this affects the calibrations that you might have to do, the amount of resolution you're able to see, and the changes in your temperature sensor. All of these things affect the operating expenses of that temperature point, as well as the measurement accuracy. And then finally, once you go digital, stay digital. Reduce the amount of error that's introduced into our temperature measurement by going from analog to digital and digital back to analog. So we have a temperature reference guide, and Jay's going to discuss a little bit more about that for you and show you what it is. But feel free to reach out to us, and we'll give you one of these free. There's a lot of good information in them, and Jay will finish us up with that.
All right, yeah. You know, we're going to go rogue. We got a question that I'm going to try to answer, so hopefully this is okay.
Okay, let's see. Okay.
Okay, hold it back here. Okay. Oh, sure. Okay, so hopefully this works out okay. We got a question about calibration, and specifically for the Texas Clean Air Board. So that's the kind of the crazy thing when I was looking at this. I mean, it's very rare that someone sends in one of our RTDs or thermocouples for calibration. Usually they use it till it burns or it burns up or something bad happens, and then they replace it. So, but if you are Southwest Research or you're selling the data, if you're doing hydrostatic testing and you have to have a certification for temperature and pressure, then you're probably going to have to show some type of certification where you validated the overall accuracy of the sensor. And there's multiple third parties that do that here locally, and we can send the stuff back as well. And there's a couple things. So what I was going to try to show, let me see how this works. If, okay. So here's a reference which pushes off this side. It's amazing what you can do with a voltmeter and some ice. So what I've got is I've got a type K thermocouple and I've got a thermocouple simulated. The difference between this little red box and my fluke meter is this has a built-in cold junction reference. When you're looking at a thermocouple, you have to have two dissimilar metals with two junctions, and the millivolts flow based on the delta T. So the easiest thing that we have is almost all the temperature curves. By the way, I don't want anyone to leave without at least knowing how to read one of the RTD curves, but I just put this in here, and this should be reading 32 degrees. If I had just taken this directly, oh, whoops. There you go. Okay, so so it's already at 33. So we're in pretty good shape because we were saying it's a 4-degree device, and already we're well within range. So to give you some idea of the response, and this is one way to do is just do an ice bath. For the Texas Clean Air Board or something else, I'm sure that you probably have to send it off for a calibration, and they would do multiple points, and you get that point either in a resistance format. I'm assuming you're using an RTD, or if you have a transmitter, they would calibrate the whole thing, which is recommended. Temperature baths are just easier, and almost all smart transducers have the ability to do, we call it trim, but you can adjust some center points. A point of interest is RTDs are quite a bit more linear than thermocouples. So usually if you get a good 0 ice bath, you're going to be in pretty good shape. Another thing that you could do is if you have the gold standard. So if you have a precision other element that's been calibrated and has a stamp on it, you can put it in the same location and use that as your third-party certification. So I hope I answered that for you, that we can do calibrations back at more industries. Typically, we try to calibrate our own stuff, but I guess would we calibrate a third party if they brought in?
Sure. Yeah.
Yeah. The only difference is, we're a lot more familiar with our transmitters than we are the other ones. But there's definitely people locally that do that business. And this is a short gap with some other things. If you had a primary standard certified that you would. So I hope that helped. That was kind of fast and furious. So let me talk about this temperature guide. And this is something that you should have on the back of your shelf. It's compact, and I like it because at the end of the day, I mean, over the last 20 years, no one really messes with cold junction reference or likes to look up the resistance chart because transmitters are so smart. They're 20-bit ADDs. They have 1 part in a million for resolution. They have isolation, which we can talk about, and the curves are built in there. But typically, if you get the 0 on, you're going to be in pretty good shape. And as I pondered, the last time I got called out on the calibration or validation for a temperature transmitter, and I just can't remember one. But anyway, this is a good guide. By the way, we have these. We will make these available to anyone who is kind enough to listen to us for the first 40 minutes, and just email us or raise your hand in the chat box, and we'll make sure that you get a copy. And I flagged just a couple of things on this. So this one is here. Where is the 3-wire? Have you got that one? Yeah. So this is probably the #1 RTD that we see. It's a 100-ohm platinum 3-wire. And hopefully we told you why that you want to use a 4-wire, because it is self-compensating. So you don't have to worry about wire length or corrosion. So this has a 385 alpha. And right over here is how it's wired up. It's not uncommon that we will get no directions. You got to do RTD, and thermocouples are very they follow a strict color standard. I'm not so sure RTDs do, but sometimes you just have to get your voltmeter out and figure where the element is at. So to go over here to resistance. Of course, we cheated, so I mean, I'll make this. We know that the reds are on both sides of the binder. The red should be shorted together, so if I put them together, I should see 0. My meter, hold faithful, so you see I'm not NIST, I'm about 3.3 ohms off. But if I put it right here, bang, I know that's it. If I take it to the white wire, I see 109. Why I only see 100 ohms? Well, at ice points is 100 ohms. So we'll talk about how to read the chart. This says that 385 alpha, and that's per ohms degrees C. So at ice point, I have 100 ohms. I multiply it by 0.00385, so that gives me a value of 0.385. So that means for every 0.385 ohms, that's 1 degree. So if we calculate it out, it's probably low 70s here. Got it? Now the other thing that we can do quickly to check is I can take each of these to ground. Thermocouples, you can ground. RTDs, you can't because it's resistance. So that's the first thing we look at. Why would it be grounded? Could have had something bad happen to it, but oftentimes in this part of the country, it just absorbs moisture. Okay, so there ends the lesson on 3-wire 385 alpha. Now, I wanted to take a look at the 4-wire devices. They can be a little intimidating. So I've got my trusty cup of water here. And I'm going to go ahead and measure this one out. So the first thing we should see, on the red wires, they should be together. Right? That's good. The white wires should be together. I said, uh-oh, broken. It's good. Remember that I had an offset of about 0.3 ohms, so they are good. So what that tells me is that the 100 ohm element is between a white wire and a red wire, if I can get it going. Okay. Now the good news is if I swirl this around, I've got it in my little ice bath here. And it was right at 100 ohms. Then I need some help. Okay, so no smoke and mirrors here. But now what I actually learned also with this is I didn't check the continuity. So this thing is performing perfectly. It's right at 100, so I would call it good. But look, when I take it to ground, I got a short. And with these ones, still only 80 ohms, so that it should be mega ohms. So, while this unit appears to work, I probably would call it out because if you put it in a process, I don't have any power supply in it, I don't have any grounding issues, but there's a good chance that there could be an issue. That's why we always, even with RTDs, because RTDs have to be floating. If they are grounded, they're not going to work. But if you can break the ground and you have an isolated transmitter, there's a chance that you're going to be okay. So that is for the RTDs. And in the book, I also just wanted to go over a few things that I highlighted. Page 9, you know that thermocouples follow a color pattern. So we know that a type K thermocouple here is yellow and red. A type J thermocouple is white and red. So that's always a good to have. Now, I highlighted these to talk a little bit about a platinum RTD. Here's the 100 ohm platinum, 0.00385 ohms per degree C. If I go down to the table, by the way, you can really mess yourself up because this only applies to degrees C. They have a degrees F table in here, but now that doesn't apply because there's what 2.3 ohm degrees per F per C. So this is how the table goes. Now, if I go at boiling point, so I didn't boil water, but the 2 points usually, if you want to fool around, got extra time, you want to do some calibration work, it's not, you can use an ice bath and you can also boil water. So 100 ohms times 0.385 would mean that at 138.51 ohm, I know that I've got a good RT. In other words, in degrees F. Type J and type K thermocouples sometimes are a little bit harder to evaluate. You know, we had done that earlier. That because you need a cold junction reference. If I had showed this one, so if I take this one in the box, whirl it around. Again, this will also give you an idea of how fast these things respond. I've got them in there. Can you imagine putting it in a thermal well? If I put my voltmeter on there, I get absolutely nothing. So I hope that would help. Please feel free to take us up on our temperature reference guide. Do we have any more questions?
Yeah, so that wraps up everything that we had for you guys. We thank y'all for attending.